Welcome. This video introduces the idea of buffer, underflow, and overflow problems. So anytime we're working with a fixed size container for data and a variable amount of stuff that we're trying to put into it, we have a potential for a mismatch. And character arrays are a classic spot for these overflow problems to arise. So this code sample has a Boolean variable. It's keeping track of whether or not I'm authorized to use a system. It has a character array to hold my name, which currently has space for 8 characters. Then we're going to go ask for my name, read that in from the console. Well, let's try this code out. So I've got the program here. If we get to the end of it after reading my name and I'm not authorized, we're going to yell at me. Otherwise, we'll say welcome to the system. So I enter my name. Andrew tells me I'm not authorized. Okay. Now let's try running it again and type a bunch of extra characters. All of a sudden, I'm admitted to the system. All right, this is not actually like some special password. No one here does it look for Andrew Scholler. Something bad happened to let me into the system. To see exactly what bad thing happened, let's go ahead and put a breakpoint in right here. And we're going to fire up the debugger. And when it comes up, what I'm going to do is go look at the authorized variable. And we're actually going to look at it in the memory editor. So right now, authorized is false. False is 0. And that is the byte in memory that's being used to hold that authorized variable. So as we go ahead and run this line of code, so I'm going to go ahead and tell this to keep running. And let me type in Andrew. So this time I'm going to type in just 6 characters. And we'll look at what happens. So we go back to the memory editor. And I can see that this is in memory where Andrew is being stored. And there's 2 more characters of space there for this character array to be stored for the 8 characters before we bleed over into the space where authorized is supposed to be. So let's go ahead and stop the debugger. And we're going to fire this up again. And so same idea, we're going to come in, we're going to look at the memory editor, right where authorized is, and I can see it's set to 0. And this time I'm going to go ahead and type in my input. That is way too long to fit in that 8-character spot. Well, scanf goes ahead and just reads in all the characters, even though they blast past where the array is supposed to end and go into the character and then past the character. So now that authorized character has a value of 104, hex 68, hexadecimal 68, which happens to be the ASCII code for character H. Now, because in C and C++ anything non-zero is considered to be true, it now thinks that I am in fact authorized. That character right there, being any non-zero value, means true. So just the process of typing in too many characters for the name overwrote the memory for authorized and changed its value. Now, because the way the data is structured, it didn't really matter what got written into that character, because anything was going to be true. If I needed to be exactly 1 for that character, well, I would just have to be more careful about what data I overflowed the character array with and make sure that that next character coming in corresponded to ASCII code 0. So this is a dangerous thing. We don't like for this to happen. And even worse than being able to change that authorized value, we can sometimes modify the code, other things about the code that's running. That's because the stack where our data is being stored for local variables contains things other than just pure data. There'll be meta information about what's going on in the program, things like where the current function should return to, data about where the parents stack information starts. And then below that will actually be our parent functions stack. So as long as we stay within the area we're supposed to, I've got this character array and I type in something like hello and it fits there, everything's fine. But if I know exactly how the memory is laid out and how much space there is for local variables, I can calculate how big an input to give the buffer to overflow with all these A's, and then place the data that I actually want, the exact hex values that I want, into somewhere like the return address. So now as this function, it's going to if this prints out the string, it would just print out a bunch of A's, and then as it tries to return, it's not going to go back to where it's supposed to go. It's going to go back to this hex address that we have intentionally placed into memory. All right, I could also overflow that and write into the parents function stack. I can do all kinds of things. Now, the operating system can do various things, and compilers can do various things to try and protect us from this kind of bug. But the potential for danger is very much there. So one of the things that we need to be very careful about is sanitizing user input, making sure that we don't trust that the user is going to type the right number of characters. If I'm using scanf, I would want to specify that I'm not just reading in any string. I'm going to read in a string that's at most 7 real characters, so there's also room for the null character. And I know that that fits in the name, and this will not try and take in more data than we can actually store. Or use some other function. Pretty much all of the C-based functions for reading into character arrays are going to give you some parameter to specify how much you actually want to read in. F gets from, I'm saying get from standard in the console into my array called name, read at most 10 characters, including and terminating null. All right, and that way I know I don't overflow that buffer. There have been a lot of kind of classic programming bugs, worms, exploits that have involved this kind of buffer overflow attack. There have also been some interesting buffer underflow attacks. You may have heard of a bug called Heartbleed in the system that we use to secure web traffic, and it revolved around a buffer underflow. So the heart of this was something that one computer could send to a server to see if it was still alive. Basically send a message, hey, if you're still there, send me the word potato, and it's 6 letters long. And so great, the server would get that message, store it briefly, and then turn around and send back a message potato. Well, what that actually looked like is we'd send a message that specified how much information we were going to send, and then actually contained the payload, the potato part of this. So if we send a message that says I'm sending you 65,000 bytes worth of information, and then we only send 1 byte, what's probably going to happen is the server is going to allocate a bunch of space to store that buffer. So we tell the server, hey, I want you to say hat and use 500 letters. The server is going to allocate 500 characters of memory. Now when it does that, it's not going to erase what's there. It's just going to say, okay, I'm using this to store your buffer. And then we only put 3 characters in there. And then the computer tries to reply back 500 characters. Well, it's going to get the 3 characters we wrote, plus a whole bunch of extra characters that may contain things like the server's private key. And great, now whoever has asked for that message has received back the server's private key. Now we can only ask for a certain amount of stuff, and so we're going to have to be kind of clever and persistent about sending these messages to get exactly what we want back. But it's a potential exploit that someone can make use of to try and retrieve information they shouldn't have by exploiting this fixed length buffer that doesn't have enough stuff in it.